Hey everyone. As promised, I was going to provide a short video, hopefully it'll be short, video on the rest of Objective 12, which is buffers, and all of Objective 13. And then I'll post another video that's focused on Objective 14, which is KSP. Okay. So let's keep going with this. I'll be using my laser pointer over here to kind of walk you through the slides, kind of like how I do in lecture. So just bear with me and, we'll go through everything one step at a time on these slides. All right, so I'm just going to start with what we talked about last time and do a little bit of a recap. You guys know I like to do this just to kind of give an overview of what we talked about on our very last class. We talked about buffer effectiveness. So what factors influence the effectiveness of a buffer? Remember what a buffer is. A buffer is something that resists change to pH, right? So it's basically a solution where you have a weak acid and its conjugate base. And if you have a sufficient amount of it in a solution, if you add some sort of strong acid or strong base, basically any sort of acid-base contaminant, you can think of it like that. The idea is that the solution, the weak acid conjugate base solution, is going to prevent the pH from going up or down. It's going to maintain that pH. Now, what factors influence the effectiveness of a buffer, right? Because the idea is it's one thing to have a buffer, but you want to have an effective buffer. And there are certain factors that influence this. There's two of them. One is the relative amounts of the acid and conjugate base in that buffer. And the second thing is the absolute concentrations of the acid and conjugate base in the buffer as well. We talked about these terms as well, capacity of a buffer, right? That's the amount of added acid or base the buffer can effectively neutralize, right? So this acid and base is not the same thing as the acid and base in the buffer. Don't get that mixed up, okay? A buffer has a weak acid and its conjugate base, right? That's what a buffer is made of. But when we talk about a capacity of a buffer, what we're saying is if we wanted to add another acid or another base to the buffer, how much, and that's what we mean by amount, of added acid or base, something else, some contaminant, and how much of that can we add to effectively neutralize that acid or base contaminant while resisting change to pH, right? Because at some point you can add way too much and you've reached the buffer capacity. You basically have went over the effectiveness of that buffer. There's also a range of a buffer, and we talked about this last time. Basically, this is the range in which a particular acid and its conjugate base can be effective as a buffer. And last time we talked about how that range is between plus minus 1, right? So if let's say you have a buffer at a pH of 5 and you don't want it to change much from 5, the ideal thing to think about an effective buffer is it's got to be within plus or minus 1 of that 5, right? So if you add enough acid, the pH is going to go down from 5 to no more than 4. It shouldn't go down more than 4. If it goes down more than 4, right, which is minus 1 of 5, it's no longer an effective buffer, right? Likewise, if you have a buffer at pH 5 and you add base, if you add too much base and it goes above a pH of 6, right, 1 above 5, then you're no longer at an effective buffer range and you've exceeded beyond the range of a buffer. So that's just to kind of recap this part of the last time we talked about this. And, we started to look in detail of what we meant by the first factor that influences the effectiveness of a buffer. So just to point back to your direction of the first reason, the relative amounts, we talked about this last time, right? A buffer is most effective, which is most resistant to pH changes, when concentrations of acid and conjugate base are equal. That's the key thing, right? If the relative amounts of the buffer components are equal, you have the most effective buffer, right? You have the best situation. And we went through two examples where that we've proved that mathematically, right? We had two separate solutions, solution 1 and 2. And we talked about how solution 1 has equal amounts of weak acid and conjugate base, and the other solution doesn't have equal amounts, right? And we looked at how we can calculate the initial pH of solution 1, because it's a 1-to-1 ratio of base and acid, right? They're the same amount. We talked about how the log of 1, right, because this ends up being 1 is 0, and then your pH equals pKa. And the most ideal buffer, the most effective buffer is when your pH equals pKa, right? Because now what happens is, if let's say I add some OH to my buffer, right, some base, this is just an example. We talked about how when we add this is going to change the concentrations of our weak acid and conjugate base, right? Because now the acid has consumed the added base, the contaminant, right? So it went from 0.100 to 0.090, right? Because we had 0.010 of the base, right? The acid ate up all of that base. So now we have this amount of acid left, and as a consequence, we've created more A- than what we originally started with, which was 0.1. Now we have 0.11. So we plug this into our Henderson-Hasselbalch equation, no longer a 1-to-1 ratio, but realize now the pH has changed to 5.09. And we talked about the percent change of this, and realize that when you calculate the percent change of the pH, it ends up being 1.8%. Not bad, right? The pH changed by just about 2% in a solution where there's a 1-to-1 ratio between weak acid and conjugate base. But then when you look at solution 2, this is not a 1-to-1 ratio, and if you calculate the initial the initial pH, you get 4.05. And now let's say you add a certain amount of base contaminant, right, strong base, to this buffer. And notice we added the same amount from solution 1 and solution 2. It's the same thing, except now the initial concentrations have changed, right? We went from 0.18 to now 0.17 as a result of adding that base. And likewise with the conjugate base, we went from 0.02 to 0.03. So we plug in our new concentrations and notice that the new pH is 4.25 relative to the initial, which was 4.05. And now when we calculate the percent change in this case, the pH changed about 5% from the initial. So bottom line is, you don't want a high percent change. You want to resist change to your pH, right? That's the whole point of a buffer. So we realized that there's less of a percent change when the ratio of acid and conjugate base is 1-to-1. And it's not so great, not as great, I should say, as when it's not 1-to-1. And we've mathematically showed that. Right, I even made a note here. A buffer becomes less effective as the difference in relative amounts of acid and conjugate base increases. Right, so we don't want there to be a difference in those amounts. We want them to be relatively the same, right, aka 1-to-1. And another thing I mentioned here is, in order for a buffer to be effective, the relative concentrations of acid and conjugate base should not differ by more than a factor of 10, okay? So bottom line is that if your base acid concentrations differ by a factor of 10, let's say the base concentration is 10 times more than the acid, or vice versa, we no longer have an effective buffer, right? That's deemed not effective. But like I said, the most effective situation is when you have a 1-to-1, equal amounts of each of them, okay? All right, and then we talked about the other factor that influences the effectiveness of a buffer, and that's the absolute concentrations of acid and conjugate base, right? What do we mean by that? What we mean by that, and we'll hit the punchline again, is that a buffer is most effective when the concentrations of acid and conjugate base are high, right? Look at this diagram over here. You see how you have a really concentrated buffer where you have the weak acid and the conjugate base, and you have more of it in the solution here than you have it over here. This is a dilute buffer. Conceptually, it makes sense that the more concentrated your buffer is, the more weak acid and conjugate base you have in solution, the more effective the buffer, right? Because if I add any sort of contaminant, like another base or another acid to this, we have more weak acid and conjugate base to neutralize the contaminant, and therefore the pH won't change very much relative to something dilute. And we talked about how the more dilute the buffer components, the less effective the buffer. That makes sense. And we showed this mathematically, right? Solution 1, we showed a case where you have the same amounts of each of these, weak acid and conjugate base, 0.5 and 0.5. But in solution 2, you have the same amounts of weak acid and conjugate base, but less, right? So 0.05 versus 0.5. And we looked at the pHs and what happens when you add the same amount of base that we added in the previous slide, right? What happens to the new concentrations? You go from 0.5 to now 0.49 and 0.51. And we see how the pH changes. Okay, and notice that it doesn't change as much when you have something more concentrated, right? More stuff, more HA and A minus versus over here where we have less HA and A minus. And you can see we calculate the percent change, right? Solution 1 has a change of less than 1%, like 0.4, and solution 2 has a change of almost 4%, right? So this is just mathematically showing you that the higher the concentration of your weak acid and conjugate base, the better your buffer, right? The more effective it is. So hopefully that makes sense. We also talked about buffer range. So we said that the weak acid and conjugate base concentration shouldn't differ by more than a factor of 10, right? I said should not differ by more than a factor of 10. And we show this mathematically, right? The lowest pH for an effective buffer is when the base concentration is equal to 1/10 of the acid concentration. This makes sense. And we can go through this mathematically and show that, if this is actually true, if you plug the base concentration in for being 1/10 of the acid, this makes sense, right? Because you realize that if your base concentration is 1/10 of your acid concentration, that means you have less base, which means you have more acid, which means you would have a lower pH, right? Now, when I plug this in, notice what happens, right? The acid concentration cancels, and now you're taking the log of 1/10, which is just -1. So this is showing you that when your base concentration is 1/10 of your acid concentration, you get that the pH is equal to pKa minus a factor of 1. And now, if you're looking at the highest pH for an effective buffer, that's when the base is 10 times the concentration of the acid, right? So you have way more base than you have acid, 10 times more. And if you're more basic, you have a higher pH. But we don't want to go over a factor of 10. That's our limit. So let's plug in our base concentration for 10 times the concentration of the acid. And there it is. We cancel the acid concentration. And now we have the pH equals pKa of log of 10, which is just 1, right? The log of 10 is 1. And now we have pH equals pKa plus 1. So bottom line is your effective buffer range is within plus minus 1 of your pKa, right? If you're going above 1 or below 1 of your pKa, you don't really have an effective buffer, and that you're beyond the range of that buffer. Okay. And then we did a practice problem on all of this. We talked about this, right? If you're given a problem, this could be an ACS question where you're asked which acid would you choose to combine with its sodium salt, which is just the conjugate base, to make a solution buffered at pH 4.25. And remember I told you guys you have these 4 acids listed with their pKa's. And I asked you, this question is just asking you, which of these would you choose to make the most effective buffer? You would want something that's closer to the pH, okay, which is this. formic acid is the closest to 4.25 of all of these. And now it's asking you for the best choice. Calculate the ratio of conjugate base to acid required to attain this desired pH. And all we really did was plug in our numbers to the Henderson-Hasselbalch equation, and we solved for this base over acid concentration. And I walked through this last class, but in doing the math, you realize that the ratio is 3.24. Ideally, you would want the ratio to be 1, right? 1 to 1. But this is the best situation you're going to get. If you tried plugging all these other pKa's in, you'll notice that the base and acid concentration is going to be much higher to maintain a pH of 4.25. And remember what we said, we don't want this base to acid ratio to be higher than a factor of 10. We don't want that. And this is within 0 to 10, so we're in a safe zone. And we have a situation where we can have as much of an effective buffer as possible. Then I had a practice question, basically the same kind of question where now they're asking you which of these 4 over here would you choose to have a buffer, to make a buffer with a pH of 7.35. And we talked about how, this is the closest one, right? Hypochlorous acid. And, you can calculate the ratio with this as well, and I think I worked that out over here. I think the question also asked you if you had 500 milliliters of this 0.10 molar solution, what mass of the corresponding salt of the conjugate base do you need to make this buffer? Okay. And pretty simple. Basically what they're asking is what concentration of base do you need? And then, what mass? They want the grams. But before you get to mass, aka grams, you need to know the concentration of the conjugate base you need to maintain a pH of 7.35. So we plug this into our Henderson-Hasselbalch equation, and we realize that if you have a 0.10 molar solution of your acid, you put that in for your acid, and there it is. Okay, and you plug everything else in. There's your pH, 7.35, that's over here. And your pKa for your chosen acid, hypochlorous acid, is 7.54. And then you're going to solve for your other unknown, which is your base concentration. And we do the math. We, take the anti-log, base 10, and we get that the base concentration is going to be 1.55. Oh, no, we're not there yet. That's 10 to the 0.19. This is 1.55. We cross multiply over here. And now we get the base concentration as 0.155 molar. Okay? Well, they told you that they have 500 milliliters of this stuff, right? So this is not grams yet. The question wanted mass. But right now we're at molarity of the conjugate base. So how do you go from molarity to mass, which is grams? Well, the first thing you can do is you can figure out how many moles of the conjugate base you have in 500 milliliters, right? Knowing that this is your concentration, you guys know how to go from volume to moles if you have molarity, and there it is. You have 500 milliliters of this stuff, convert it to liters, and then use the 0.155 concentration to get moles of your sodium salt of this, right? It wouldn't be HClO, it would be now sodium NaClO minus, right? Which is sodium and its conjugate paired up with the conjugate base, ClO minus. Shouldn't be a negative there, sorry. It just should be NaClO, no negative, right? Because the negative is balanced out with the positive sodium, so that negative shouldn't be there. It's not over here, so I didn't make that mistake here, but bottom line is now you can take the moles of that sodium salt of the conjugate base, right? And use the molar mass of this to get grams. And there we go. All right, this is just showing you another example problem of a buffer question. And you might see this kind of question on the ACS, but you just need to be aware that if you find a acid that has a pKa close to the pH of the buffer that you want, that is the acid that you're going to choose, right? You want an acid with a pKa that's close to the pH of the buffer that you want, okay? And once you identify that, you can then use the Henderson-Hasselbalch equation to solve for any of these variables that a question might be asking you for. It all depends, right? In this case, they asked for the base concentration, but even more so, they asked for the grams of this base that you need in 500 milliliters to make a buffer with a pH of 7.35. Okay? Really try to understand what the question's asking you, and don't let that fool you. All right, and then we talked about titrations. So remember what we said, what a titration even is? Titration is basically saying that if you have some sort of unknown concentration, take a look at this, an unknown concentration of acid, in this case H+, and this could also be an unknown concentration of a base, doesn't matter. Bottom line is this is an unknown concentration, and the only way you can figure out what the concentration of this actually is by titrating it with, in this case, a base to neutralize the unknown concentration of your acid, right? And then the idea is that if you write, acid plus base makes water and a salt, and that's, we don't really care about the salt, we just care about the acid and the base. And really this is just H plus OH minus makes water, right? And the H plus and OH minus in this case are 1-to-1 ratio, right? They're a 1-to-1 ratio. So if I know how much base I needed to add to neutralize all of the acid in my unknown concentration, well, that's great, because now I know there's a 1-to-1 relationship between the two, right? So I can actually solve for my concentration of my unknown acid by knowing how much base I added to this to neutralize all of it. And we talked about how in lab the way you knew you neutralized all of the acid is if you get a pink color, right? But like I said, sometimes you don't really care about, the end point or the equivalence point where you've consumed all of your acid. Sometimes what we care about is the pH along every single volume of sodium hydroxide. So what happens to the pH with every single drop that you add of the base to your acid? And you can track that, right? You can graph it and you get this characteristic S-shaped curve. Remember what I said, the x-axis here, volume of sodium hydroxide, y-axis is pH. So if you track the pH of this as you add more base, the pH is only naturally going to go up, right? Because you're making this more basic. The more base you add, the higher your pH is. But when you're trying to neutralize an acid with base, you're going to get this characteristic S-curve. This is how the pH is going to change. And the equivalence point is right in the middle over here. This is the point right over here where all of your H plus has been consumed by your OH minus and turned into water. Okay. So we talked about what happens when you titrate a strong acid with a strong base. We talked about the equivalence point, and we kind of go deep into what that is and how we can calculate the equivalence point. So notice the situation. I have a 25 milliliter solution of a 0.100 molar HCl. Okay. And I know my concentration of the base that I'm adding to this to neutralize it. Now, in this case, we know the concentrations of each, right? The question is, how much of this do we need to neutralize all of the acid? Okay. And it turns out that this is a pretty easy problem, because if the concentrations of each of these are the same, the amount of volume that you need to neutralize all this is going to be 25 milliliters. So you're going to be, basically what I'm saying is you need 25 milliliters of this stuff to neutralize all of this. And why this makes sense? Well, let's talk about it again. So right now, the first thing I want to know is how much HCl do I have in this. And I know it's 25 milliliters of this, but particularly what I want to know is how many moles of HCl do I have in this flask? Because if I know how many moles of HCl I have in this flask, if I know that number, and I know that there's a 1-to-1 ratio between HCl and NaOH, right? Based on this equation, HCl plus NaOH makes water and a salt. If I know there's a 1-to-1 ratio between these two, I know that for whatever amount of moles of HCl I have, I need the same exact amount of moles of sodium hydroxide to neutralize all of the acid. Okay? And how do you calculate moles of HCl? Well, you guys know that if you take a volume and you multiply it by the concentration, you can get moles, right? And here's the calculation, right? We just converted 25 milliliters to liters and then multiplied it by the concentration, moles over liters. The liters cancel. And now we're left with this amount of moles of HCl. Now we just said that we need the same exact number of moles of HCl as we do NaOH. Or vice versa. We need the exact amount of moles of NaOH as we have HCl. And there it is, right? Here's your moles of NaOH, and I'm trying to figure out the volume that I need to titrate this 25 milliliter solution. So again, I'm using the concentration here. Okay, and there it is, 0.100 moles per 1 liter. Obviously, this is the reciprocal because we want to cancel the moles out to get liters. And there we have it, right? 0.0250 liters of sodium hydroxide to neutralize all of this acid, which is basically 25 milliliters. So we just proved mathematically that the equivalence point, which is the point that all the number of moles of added base equals the amount of acid, is at 25 milliliters in this case. All right, so it's nice that we know the equivalence point because that's kind of like going to be like our reference point, right? Now, let's talk about how we're going to build this titration curve because we said it's going to be an S-shaped curve, right? We said that. So the initial pH before we add any base. So basically what this is telling me is what's the pH of this before adding any of this? Well, that's pretty easy because HCl is a strong acid. And if HCl is a strong acid, we know that all of the HCl that we have is going to convert to H plus and Cl minus, right? So if I have 0.100 molar HCl, I know that I have 0.100 molar H3O plus, right? Now I'm going to take the negative log of this to get the pH, and it's just 1. Okay? And there it is. That's my first point on my titration curve. All right, now we're adding 5 milliliters of sodium hydroxide. So finally, we're starting to add some base, and particularly 5 milliliters of it. So what's the pH now after we add 5 milliliters of base? Well, the first thing I want to do is figure out how many moles of sodium hydroxide did I actually add, right? If I added 5 milliliters, that's great, but how many moles are in 5 milliliters of sodium hydroxide? That all depends on how concentrated that sodium hydroxide is. And in this case, it's 0.100. So I can get moles of sodium hydroxide, right, knowing that I had 5 milliliters, which I converted to liters right over here, times the concentration to give me the moles of hydroxide that I added to my acid flask over here. And I make a reaction table, and I show how you start with 0.00250 moles of your H3O, right? Because that's basically what this is the amount of moles that's in here, right? This is the amount of moles of acid that's in this flask. And now we know we have a certain amount of moles of base that we added to it. So what's going to happen? All of this acid is going to consume all of this base and turn it into water, right? Now, how much acid do we have left? Well, let's just take the amount of acid we started with, which is 0.00250, and subtract it by the amount of base that we added, which was 5 milliliters, but in this case, it's this amount of moles of OH minus. And this is how much H3O we have left. right? This minus this. And now we have the moles of H3O left, but we need concentration. Concentration is moles over liter, not just moles. So what we're going to do is we're going to take this number right over here, and you're going to divide it by the total amount of moles. The total amount of liters, the total amount of volume, right, which is 25 milliliters that we started with right over here. That's the initial volume, plus the added volume, which was 5 milliliters from this burette. So the total volume of the solution now is 25 milliliters plus 5 milliliters, which is just 30 milliliters or 0.0300 liters. And now we can get moles over liter. This is our concentration in molarity of our H3O. And we take the negative log of it to get the pH, which is 1.18. And now we plot it on our titration curve. Now it went from 1 to 1.18. Notice it barely changed. And this is good because this is kind of like a buffer region, if you will. Although this is a strong acid and strong base, so it's technically not a buffer, but we haven't changed the pH that much, is the idea. All right, so what happens with the pH after adding 10, 15, and 20 milliliters? Well, it's the same kind of calculation, right? Same thing. Just like the math we did in the previous slide, where we added 5 milliliters of sodium hydroxide, you do the same kind of math for adding 10, 15, and 20 milliliters of sodium hydroxide. And why is it the same math? Because this is all before the equivalence point. Guys, remember that the equivalence point was 25 milliliters, but we're before the equivalence point. So before the equivalence point, the calculations are going to be exactly the same. And if we do the exact same style of calculations, we're going to get these pHs at these different volumes. And it makes sense that we're going up in pH slowly. We're not at the equivalence point yet. And we plot these points, right? The pH is getting higher as we add more base. So this looks pretty good. Okay, now we got the pH after adding 25 milliliters of sodium hydroxide. Remember, at 25 milliliters, this was the equivalence point. And what I told the class last time is that the pH at the equivalence point of any strong base, any strong acid, strong base titration will always be 7.00. Always. And we talked about why. Right? If you're at the equivalence point, what happens? That means that you've consumed all of your H plus with OH minus. And if you have no H plus and no OH minus, they completely neutralize each other to make water, then you just have a neutral solution, which is a pH of 7. And remember, the only way that you can have any H3O with a pH that's 7, well, basically you just have water, pure water. The only H3O concentration you get from pure water is the autoionization of water, which is just water reacting with water, right? And when water reacts with water, you make H3O plus and OH minus, and you make very little of it. And we talked about this, how that's basically the equilibrium constant for water, Kw, which is 1.010 to the negative 4, is equal to H3O plus times OH minus concentration. And we know that when these concentrations are the same, you know, it's basically 1.010 to the negative 7. And you take the negative log of that, and that's just pH 7. Okay? And this is going to happen for any strong acid, strong base solution. It doesn't matter what it is. Right? Because with every strong acid, strong base titration, you're accomplishing the same thing. Where at the equivalence point, you're at pH 7. You're neutral. And the only H3O you're going to have is from the autoionization of water. So here's our equivalence point. We plotted it. It's right over here. Big jump, right? We went from not increasing the pH much to finally going up and reaching the equivalence point. All right, what about a pH after adding 30 milliliters of sodium hydroxide? So now we're above the equivalence point. And I want to show you something interesting. What happens when you go above the equivalence point? Well, Now, if you're adding 30 milliliters of sodium hydroxide and it has a concentration of 0.100, how many moles of sodium hydroxide do you have? Well, we can calculate that, and we got 0.00300 moles of hydroxide in 30 milliliters. That's how much we're adding to this. And what's the effect? Well, I know that I started with 0.00250 moles of the H3O, right, in this flask. And I have 0.00300 moles of my base. And the acid's going to eat up as much base as it can, but notice there's more base this time than there is acid, which makes sense because at the equivalence point, you don't have any more acid left. And if you're adding an extra 5 milliliters, right, 25 is what the equivalence point was, and you're adding another 5 milliliters, which is 25 plus 5 is 30. So you obviously have more base than you have acid now. And this is how much base you have left. And you have no acid left. So now I have a solution that's basic. And the question is, what is the OH minus concentration right now that we have leftover base and nothing else? We got moles right now, but let's go from moles to molarity to get concentration. We need moles over liter. And obviously, if we're going to consider the volume, we need to add up all the volumes from what we originally started with, which was 25 milliliters, right? That's right over here. And we added 30 milliliters of base. So in total, we're going to have 55 milliliters, right? 30 plus 25, or in this case, if it's liters, it's 0.055. So now we have our OH minus concentration, right? Moles over liters, and here it is. And now we can get the pH from this, right? And there's several ways you can go about it. The example I show here is using the KW expression. You don't have to do that. You guys can get the POH first and then get pH. But bottom line is you end up having the same number anyway of 11.996. Pretty basic, right? Which makes sense because you have no acid left, but you have base, and there's your plot right there. So notice we're almost done completing our titration curve here, right? If I go to the next slide, you can calculate the pH after adding 35, 40, 50 milliliters of NaOH. It's the same kind of math that you did in the previous slide, same concept. You can calculate the pH the exact same way, doing the same kind of math, and you're going to get these numbers at 35, 40, and 50 milliliters. These are your pHs, and you're going to add that to your curve. And now you're pretty much done, right? You finish the curve, and now you can trace the curve out. And there it is. There's the overall pH curve. We draw the line, and notice this is our initial pH before we added any base. And then we started adding some base, and notice that at this point we still had H3O in excess, right? We didn't consume all of the H3O that was in here. So we're before the equivalence point here. Now we reach the equivalence point. It's always going to be 7, right? For a titration of a strong acid with a strong base. And then after the equivalence point, the OH minus is in excess, right? So that's just to kind of summarize the pH curve and how we were able to do various types of math to be able to get to the pHs at every single point here, okay? All right, now I think where I left off with you guys really last time, and I know I went through basically 40 minutes of recap, but I figured it was worth doing that because my 9 a.m. and my 10 a.m. section don't, easily overlap, so I don't always get to talk about, exactly what I did in my 9 a.m. as my 10 a.m., so I'm just going to go through the entire Objective 13 titrations with you, even though I talked about this last class, but I'm going to iterate some of the same stuff just to kind of keep consistency with both classes. So in this slide, basically what I'm showing you, you just saw this. Okay, I just showed you this. This is a titration of a strong acid with a strong base. That's what the curve looks like. This was in the previous slide. What I'm showing you now is what if you have a titration of a strong base with a strong acid? So it's the reverse situation, right? To basically give you an idea, instead of this being base, this is now acid, and you're titrating base. Imagine this wasn't acid anymore. This is base. This solution is a base, not an acid. So you're going to titrate base with acid. And what is your pH curve going to look like? Well, it's going to basically be the reverse situation where you start, here's your initial pH with no volume of HCl added, right? 0. At 0, you just have strong base. You don't have any acid. You're not adding any acid yet. So obviously your pH is going to be really high, really basic, because you haven't added any HCl. But you're going to go down an S-curve fashion in the same way that you go up in an S-curve fashion. In this case, you're going down in an S-curve fashion. All right, and there's the equivalence point. You can probably guess that over here in this region, you have OH minus in excess, right? We didn't add enough acid yet over here to consume all of the OH minus. At the equivalence point, we've consumed all of our OH minus. And now over here, you have excess H plus from your HCl, right? So same idea. Okay, then we had a practice problem. So a 50 milliliter sample of 0.200 molar sodium hydroxide is titrated with 0.200 molar nitric acid. Okay, so what do we got over here? We got a strong base, sodium hydroxide, is being titrated with this concentration of acid. Okay. Calculate the pH after adding 30 milliliters of HNO3. So at this point, 30 milliliters, the question is, are we above the equivalence point? Are we not? Well, what do you think the equivalence point would be? The equivalence point would be when you add 50 milliliters, right? Because check this out. You have 0.200 molar of your sodium hydroxide, and your 0.200 molar nitric acid, your strong acid, it's the same concentration, right? 0.2 and 0.2. And we just saw that when we have equal concentrations of strong acid and strong base, it takes the same volume to titrate it, right? In our case earlier, we had a 25 milliliter solution, and the equivalence point was 25 milliliters. Well, now we got a 50 milliliter sample, and the equivalence point is going to be 50 milliliters. So right away, I know that when I look at this, I'm like, okay, after adding 30 milliliters, I haven't reached the equivalence point yet. The equivalence point is 50 milliliters. I only added 30. So conceptually, I know that, I haven't consumed all of my sodium hydroxide. There's going to be some sodium hydroxide left because we didn't add enough to consume all of it yet. Now, the question is, how much sodium hydroxide did I even start with, right, from a moles perspective? Because we have molarity and we have milliliters, but we can convert to moles, right? And we've done that. You just take your 50 milliliters, convert it to liters, multiply by your concentration, 0.2, and there's the calculation right over there. And here's how many moles of OH minus you started with. That's in your 50 milliliter sample right there. And you can make a reaction table where you show that the base is reacting with the acid, and you know you're starting with this amount of base. And the question is, how much acid are you starting with? Well, you know you're adding 30 milliliters of a 0.200 molar nitric acid solution. You can calculate the moles of the acid in the same way you calculated the moles of the base. There it is. So initially, before the addition, you had 0 acid, but now you've added 0.00600 moles of your nitric acid, and your base consumed all of it, right? The base basically ate up all of this acid, and this is the amount of base you have left. Again, we didn't reach the equivalence point. We didn't reach the point where we consumed all of the base. We're going to have a little base left, and there it is. And now I want concentration of it, so I'm going to divide it by the total volume. Right? The volume that we started with, which was 50, plus the 30 that we added to get the total concentration. And there it is. And you end up with a OH minus concentration of 0.0500. Now from there you can calculate the pH. Notice the way we did it here in this case, just taking the negative log of this OH concentration to get POH, and then getting pH from POH by 14 minus that, and you get 12.70. So you can do this for any point, but it's always good to know, guys, when you have a titration problem, it's always good to know where the equivalence point is first, right? You want to calculate that. And I know in this case it's pretty obvious because we know it's 50 milliliters. We didn't even have to do any math. But if you had to do the math to calculate the equivalence point when the concentrations of base, strong base, and strong acid are different, it's not the same, well, then you know what kind of math you need to do, right? And I'll go back to the slide just to kind of recap. How do you calculate the equivalence point? There it is. Right? So what's the first thing you want to do? The first thing you want to do is you want to calculate how much HCl or base, whatever you're titrating, you have in the first place. So get the moles of that, and then look at your equation. If there's a 1-to-1 ratio between your acid and your base, well, you're like, okay, great. If I know I have this amount of acid, I need exactly that amount of base to titrate all of this. All right, so let's go back to our example over here. Our practice problem. Right, we know we have this amount of moles of OH minus. So how much H plus do I need to titrate all of this? So it's the exact same. Right, if I show you the equation between HNO3 and sodium hydroxide, let me draw it. Let me go back to the pen option. So imagine you have NaOH, right? This is aqueous, plus HNO3. HNO3. You always want to write this out because the thing is, if you don't write out the equation, it can get confusing. Like, oh, is this a 1-to-1 ratio? Right now, we're assuming it's 1-to-1, but let's prove that. Right? So let's do a double replacement reaction. We make water, right? Every time you add an acid and a base, you make water, which is a liquid, and a salt, which is sodium nitrate, NaNO3. And this equation is balanced, right? We don't need to add any coefficients in front of any of these, so everything's 1-to-1. Oops. Oop, that's not what I wanted. One to one. To 1-to-1, right? Everything's 1-to-1. But bottom line is that, between base and acid, that's what we care about. It's 1-to-1. Okay? So we need as much acid to neutralize all of that. Okay? 0.0100. So, you can now figure out the equivalence point by just taking the volume that you need, which you just use the concentration, right? Imagine the concentration was different in this case. Let's say instead of it being 0.2, let's just say it was like 0.100 molar nitric acid, which is just HNO3. So what's the equivalence point now? Well, if I take 0.0100 moles of my HNO3 or H plus, right, because it's a strong acid, so HNO3 completely dissociates into H plus. We're going to be like, okay, we know that for every 0.100 moles, I have 1 liter, right? This is from this now. So now what's my new equivalence point? Well, 0.0, whoa, that's not what I wanted. 0.0100 divided by 0.100 is just going to be 100 milliliters, right? So now my new equivalence point is 100 milliliters. You guys see the trend, right? That the less concentrated your acid is, the more volume you need to titrate the base, right? The less concentrated this is, the more volume I need to eat up all of that, right? And in this case, it's 100 milliliters now. Before it was 50, right? So you can make sense of that. Guys, it's always good to conceptually think about these problems, right? Like when you're doing math, it's great to do all the math and, get all the numbers, but you need to think to yourself, do the numbers make sense? Right? Every time you get a number, you need to ask yourself, does this number really make sense? All right, let me go back to the pointer. Okay, so now we're going to talk about the titration of a weak acid with a strong base. So basically, it's very similar to the titration of a strong acid with a strong base, but there are some differences. And the key differences here is that you're dealing with a weak acid. And weak acids, we know, don't completely break up into H plus and A minus, right? And we know what happens when we have a weak acid. We need to make ice tables, right? So whenever you're doing a titration of a weak acid with a strong base, or let's say a weak base with a strong acid, you always got to do an ice table of the weak acid or weak base, depending on your situation, right? Because we know that weak acids or weak bases, don't completely break up into their respective components, right? So ice tables help figure out how much the weak acid or the weak base actually like dissociates, right? And we have to apply that logic in this titration problem. So let's say I have a situation where I have 0.100 molar sodium hydroxide, but now I'm not titrating a strong base, I'm titrating a weak acid. And here it is. This is the example. It's HCHO2, okay? Now remember the first thing we always want to know. We want to know what the equivalence point is, right? What is the equivalence point here? And you can guess it, right? Check it out. These concentrations are exactly the same, which means what? It probably takes as much base as there is acid, which is 25 milliliters, to titrate and consume to neutralize all of the weak acid. Okay, so bottom line is this is really easy again, because if the concentrations are the same, it's going to take as much volume to titrate all of this acid. So 25 milliliters of your base is going to neutralize 25 milliliters of your weak acid because they're the same concentration. And we can show that mathematically, right? This is the same math that we did in the last couple of slides when we looked at equivalence point for strong acid and strong base. The pH is going to be different, right? We said that for a strong acid, strong base, the pH at the equivalence point is always 7. But it turns out that the pH of a weak acid, strong base solution is not always 7, right? And we're going to look at that. But right now, we're just trying to figure out the volume of sodium hydroxide required to reach the equivalence point. And if you really want to calculate it, let's say these concentrations were different. This is how you would do the calculation. We just saw this. The first thing you want to do is figure out, okay, how many moles of weak acid do I even have? And how can I extract that information from the volume and the molarity? We just multiply them two after you convert milliliters to liters. We saw this 1,000 times already. And here's moles of your acid. Now, if there's a 1-to-1 ratio between your weak acid and your strong base, then, you basically need this exact amount of this same exact amount of base to neutralize all of this acid. Okay? And we confirmed the 1-to-1 ratio right over here. You guys need to understand that whenever you're trying to figure out the equivalence point, the first thing you want to do is figure out how many moles of the thing you're titrating you have in the first place, right? How many moles you're starting with for your titration. And then once you know that, you need to figure out the mole-to-mole ratio between the thing that you're titrating and the thing that you're using to titrate it, right? Which in this case is weak acid is being titrated with strong base. And the question is, does the weak acid and strong base have a 1-to-1 relationship with each other? The only way you really know that is by writing the equation out. Okay, so what's the first step in determining the equivalence point? Again, the first step is figuring out the amount of moles of weak acid that you have. And then once you have the moles of weak acid, knowing the mole-to-mole relationship between your weak acid and your strong base. if it's a one-to-one relationship, it's really easy, right? Because you need as much strong base as you have moles of weak acid to neutralize it, right? But if you don't have a one-to-one ratio, then what do you need to do? Well, you need to multiply this moles of weak acid by the mole-to-mole ratio of your acid and your base. Okay? So, in this case, it's a one-to-one ratio. It's pretty simple. Now we just take the moles of sodium hydroxide, right, which is equivalent to the amount of acid we have. And we're going to figure out the volume of sodium hydroxide that we need, and we come to the conclusion that it's 0.0250 liters when you do the math, just like the math we did previously. So in this case, it's 25 milliliters of sodium hydroxide to titrate 25 milliliters of weak acid. Okay. And I make a note here. I say that the volume at the equivalence point does not depend on the identity of acid that you have, right? It doesn't matter if it's strong acid or strong base. It doesn't matter if it's strong acid or weak acid, right? It does not depend on the identity of the acid. It depends only on the amount in moles of acid present in the solution before the titration even begins, and on the concentration of the added base. Okay, this is just a statement summarizing everything I talked about for this slide. Okay. All right, so what's the initial pH before adding any base? So realize we're not adding any of this base yet from this burette. We're just trying to figure out the pH of this concentrated weak acid. And the way you do that is you set up an ice table. Okay. We've done these acid tables maybe a gajillion times at this point. Here it is. This is just me showing the dissociation of our weak acid. We started with 0.100 molarity, right? We have initially 0 of the acid and conjugate base, H plus and conjugate base. Here's our change. Here's our equilibrium concentrations. We've seen this many times before. You can solve for this. And obviously, you would need the Ka, right? The Ka of this would be given to you. In this case, is 1.8 times 10 to the negative 4. You write your equilibrium expression, right? You put in your x values at equilibrium into your expression. You make the x a small approximation. And then you carry out the math and solve for x, and there it is. So x is your H3O concentration. Remember, you're trying to find the pH, so you need the H3O plus concentration to get pH, and your X is your H3O plus concentration. So once you get X, you can take the negative log of that, and you get 2.37. Okay, so that's your initial pH, and we're going to put it right on our plot over here on our titration curve. Right, so realize when we had the titration of a strong acid with a strong base, it was really easy. We knew the initial pH because, you just take the negative log of that strong acid concentration. But whenever you have a weak acid, you can't just do that because you know that not all of the weak acid is going to turn into H3O and conjugate base, right? So that's why I need to set up an ice table, is to know how much weak acid actually dissociated. And this is the math to do that. So you guys have done this. This has been on your exam. This is easy to get the initial pH. But now what happens when you add 5 milliliters of sodium hydroxide to your weak acid? What happens now? Well, we're going to do the same exact thing we did last time, guys, where we figure out how much moles of sodium hydroxide we added to this, right? Adding 5 milliliters is great, but how concentrated is this thing? It's 0.100 molar, right? So how many moles of sodium hydroxide did we add to this? We added 5 milliliters, but how many moles of sodium hydroxide are in 5 milliliters? The only way we can do that is to multiply this number by our concentration. And we've seen that math already before, and we get that the OH minus concentration in the OH minus moles in 5 milliliters is 0.00 0.0500 moles. Okay, right? Initially, you didn't add any before addition. After the addition, you added 5 milliliters, and this is the amount of moles that's in 5 milliliters of NaOH. And what do you think is going to happen? Well, the weak acid is going to consume all of this base, right? There's more acid than there is base, so the acid is going to consume all of this base, and you're left after the addition with none of the base anymore. And the acid consumed all of this, so the acid concentration, or excuse me, the amount of moles, I should say, of acid you have left is this minus this number, which is 0.00200 moles now. And as a consequence, you've now turned the HCHO2, the weak acid, you've turned that into conjugate base. How much have you turned this into this? Well, if this acid ate up this amount of base, that means that this converted to the weak conjugate base as a result of consuming the base, right? So now you have 0.000500 moles of your conjugate base, okay? So there's your ratios, and you're probably wondering, can't I just get the molarity now? And you could do that, that's fine. But remember what we said is when you have a weak acid and a conjugate base, you potentially have a buffer, right? They're not equal concentrations. Remember, they don't have to be equal concentrations. And basically what this is telling you is you can bypass the ice table and use the Henderson-Hasselbalch equation, right? How do you know when you can use the Henderson-Hasselbalch equation? This is it right here. This is the Henderson-Hasselbalch equation. How do you know when you can use this? You know when you can use this when you have a weak acid concentration and a conjugate base concentration. Now, this isn't concentration. This is moles. I know it's moles, right? It's not concentration yet. But you have some amount of weak acid and the conjugate base, right? If you want to get concentration, you can do that. Sure, divide liters over moles to get concentration. And in this case, it's just 25 milliliters plus the 5 that you added. That's going to be 30 milliliters, and you convert to liters, and you can get concentration. But the thing is, we don't have to do that, because it turns out that if you plug this into your Henderson-Hasselbalch equation, we showed that the 30 milliliter part cancels anyway. So you can forget about that. You can just plug in the moles in your Henderson-Hasselbalch equation, and you'll get the same answer. I can guarantee it. You can try it both ways, and I can guarantee that you can bypass, converting moles to molarity. You don't need to do that when you're using the Henderson-Hasselbalch equation. But bottom line is, you can use the Henderson-Hasselbalch equation when you have some amount of weak acid and conjugate base. And those are the amounts. You plug it into your equation. The pKa of this is 3.74. And how would you know that? Well, the problem would have to give you some information. They'd have to give you at least the Ka of the weak acid that you're titrating, right? And there it is. And you can convert to pKa by just taking the negative log of this, right? So that's 3.74. You do the math, and you get that the pH is 3.14. And yet we have another plot on our curve after adding now 5 milliliters of sodium hydroxide. So let's keep going. Now, we have a pH after adding 10, 12.5, 15, and 20 milliliters. And we do the math the same exact way that we did it before. We're using the Henderson-Hasselbalch equation, but obviously we need to draw that reaction table for each of these volumes like we did before, right? This one was for 5 milliliters, but you do the same thing for 10, 15, 20, right? And you do that, there it is, right? And notice this is interesting. Over here, we're at half of the equivalence point. Half, right? What that tells you is now, halfway at your equivalence point, you have equal concentrations of your weak acid and your conjugate base. That makes sense, because at the equivalence point, you've consumed all of your weak acid, right? At the equivalence point, your base ate up all of your weak acid. It's gone. But at halfway of your equivalence point, half the equivalence point, which in this case is 12.5 milliliters, right? We said that the equivalence point is 25 milliliters, right? Just like the first problem. Half of the equivalence point is half of 25, which is 12.5 milliliters. And at halfway the equivalence point, you've consumed half of your weak acid. And now you have conjugate base and weak acid in equal concentrations. And remember the ideal situation of a buffer. The most effective buffer is when you have equal amounts of each of these, right? We saw this in the beginning of this segment. When the pH is equal to the pKa, it's when the concentrations of your weak acid and your conjugate base are the same, okay? So that's half the equivalence point, and you can go on and calculate the pH using the Henderson-Hasselbalch equation for pretty much every single point before the equivalence point. And notice that the ratios of weak acid and conjugate base change as you add more base. It makes sense that your weak acid concentration after your half equivalence point is getting lower and lower, right? You're adding more base, the acid's going down, your conjugate base concentration is going up. And likewise, your pHs are going up as a result of adding more sodium hydroxide. Okay? All right, now we're at the equivalence point. And what happens at the equivalence point? Remember what I said. At the equivalence point, all of your acid is consumed. It's gone. All of the base that you added at 25 milliliters, right? We said 25 milliliters is the equivalence point in this case. All of that 25 milliliters of base ate up the 25 milliliters of acid, right? And they're equal concentrations. And when we've consumed all of our acid, what happens? Well, if all of the H from HCHO2 is gone, the only thing we have left is CHO2 minus, right? The H is not in front of there anymore. And what that tells me is that if I started with this amount of acid and I've consumed all of it, all of this had to convert to its conjugate base. And we have absolutely no more acid left at our equivalence point because the base, we added enough base and exactly the enough amount of base to eat up all of our acid. So the only thing we have left floating around in this flask over here is conjugate base. And the question is, how much of this conjugate base is going to convert back to HCHO2 spontaneously, right? Like, how is this going to happen? How much of this is going to go towards the right? And notice I have an equation here to show that. I have my conjugate base, which is all I have left in the solution. That's it. And it's in water, obviously. And the only thing it can do, the only thing it sees, the only thing that it can react with, the only available thing that it can do anything with is H2O, water. And then when it reacts with water, it can potentially reform some of the weak acid and OH minus. The question is how much, because this is an equilibrium. And the equilibrium is barely going to the right? Because the Ka is going to be really small, and you can probably guess that the Kb is going to be really small too. So bottom line is barely any of this is going to make, go back to the weak acid, barely. And we need to calculate how much. And the only way we can do that, whenever we know we have a small amount going to the right, we need to draw an ice table to figure out how much went to the right. We know that we started with 0.0500. How do we know that? That's not this number, right? But remember what this is? This is molarity and this is moles. So if we convert this to molarity, that's just dividing it by the total volume. What's the total volume? Well, we started with 25 and we added another 25 of the hydroxide, right? So 25 plus 25 is 50 milliliters. Convert that to liters and then take this number and divide it by, 50 milliliters, but convert it to liters, right? 0.050. And you're going to get this molarity for your concentration of your weak base. Initially, you have none of the acid and the hydroxide, and then you go through your change, minus x plus x plus x. Here's your equilibrium concentrations. And now let's calculate what x is. Well, we know that we're talking about an equilibrium for a conjugate base. And if, let's say, the problem gives you Ka, that's the equilibrium, constant for an acid, not base. So what do you need to do? Well, whenever you're doing an ice table for a conjugate base, you need to convert the Ka to Kb, right, for base. And we know that Ka times Kb is Kw. We've saw this before. You know what Kw is. That's a constant. It always is 1.0 10 to the negative 14. Divide that by Ka to get Kb. And here's your Kb. Okay, you're going to use that Kb. That's going to equal your concentration of products divided by reactants, which in this case is x squared divided by 0.0500 minus x. You can make the x a small approximation and, cross multiply, solve for x. You get your x. You can check the 5% rule. The approximation should work, right? Because, Kb is so freaking small. Look at that, right? So you got your x, and x is your OH minus concentration. There it is. And now you can solve for your pH, right? You can either get the POH and then solve for pH, or you can do what I have on the right over here, which is use the Kw expression, solve for H3O, and then take the negative log of that H3O concentration. You should get 8.23. Okay? So check this out. The equivalence point is not 7, right? We just said that the equivalence point for a strong acid, strong base, is always 7. But now when you have a weak acid and a strong base, the pH at the equivalence point varies, right? And it all kind of depends on the weak acid that you're dealing with, right? Every weak acid is going to have a specific, Ka, and, you're going to solve for X and do the ice table, yada, yada, and you're going to get a different pH every time. And in this case, the equivalence point is 8.23. Okay? Great. Now we're beyond the equivalence point, and you can guess it. Above the equivalence point, you're out of acid, you're done. You have no acid left, right? At the equivalence point, you're done. Now that you're past the equivalence point, you're adding excess OH. And if you're adding excess OH, the question is, how much OH minus is left after all of the acid has consumed as much base as it can? And guess what? This is it. You just do the math. This minus this number is going to give you that amount of base that's left. And you're probably wondering, well, wait a minute. I also have conjugate base. And what's going to be more influential to the pH? Is it going to be the OH minus concentration, or is it going to be the conjugate base of the weak acid, the concentration of that? And the answer to that question is, which one's stronger? Which base is stronger, OH minus or this conjugate base of the weak acid? It's always going to be the strong base, right? That's what's going to influence the pH the most because it's stronger. So bottom line is, this is going to make a very small contribution to the pH relative to the amount of this. This is going to make way more of a contribution to the pH because this is a strong base. It's way stronger than this. So really, you base your pH off of the amount of strong base that's left in your solution, and it's this amount. And if you're trying to get a concentration, you got moles right now, you're just going to divide this number by the total volume of your solution, which is what you started with, 25 milliliters plus the 30 milliliters that you added. And there it is. And there's your concentration of your OH minus. And, you can solve for pH from there. Either use the Kw expression or get the POH from OH minus and then get the pH. You guys know the drill. There it is. There's our point 11.96. Guess what? We're almost done with our curve, right? Very similar to what the curve looked like last time. And you can guess it that if you want to calculate the pH at other points above the equivalence point, at 35 mils, 40 milliliters, 50 milliliters, it's all the same stuff. Because now above the equivalence point, you have excess strong base. And that excess strong base, OH minus, is going to influence the pH much more than whatever conjugate base that you formed, which is the maximum amount that you can form is the 0.0, what was it? 0.00250 moles. That's the most conjugate base that you could make because you only had that amount of acid to start with, right? So, you just keep going up in OH minus concentration, and obviously your pH is going to get higher and higher with more volume of NaOH that you add. And there we plot those are the last points. And there's your overall pH curve for the titration of a weak acid and a strong base. Looks pretty similar to strong acid, strong base. What's the only difference here? Well, the biggest difference, I would say, between the titration of a strong acid and a strong base versus a titration of a weak acid and a strong base, the biggest difference between the two is the equivalence point. The equivalence point is not 7, right? If you're given an ACS problem and they show you a titration curve and you notice that at the equivalence point it's not 7, you already know that it's a titration of a weak acid and a strong base. You don't need to really know any other pieces of information, right? If you look at the equivalence point, that already tells you a lot about what you're dealing with, right? What these solutions are, like what the identity of them could be. But the other parts are very similar, right? You have a buffer range, right? This is where the pH is barely changing, right? A buffer, by definition, is a region. A buffer range is a range where the pH doesn't change, right? Resisting change to pH. There's your buffer range. There's your equivalence point. And then at this point, you just have, excess OH minus. All right, you can guess it. I already showed you what this was in the last slide. But what if you're titrating a weak base with a strong acid, so the reverse? And you can guess it, the curve is going to look kind of reverse, right? Where now you're starting really basic, right? Because you have a weak base. And you're titrating the weak base with a strong acid. So the more HCl that you add, right, the more strong acid that you add, the more acidic you're going to get. Your pH is going to go down. And it's going to go down in a very similar fashion. Here's halfway of your equivalence point, and there's your equivalence point. Right? And check this out. It makes sense that the equivalence point is going to be, 5.28. Versus your equivalence point over here is basic. It makes sense because if you're adding a strong base to a weak acid, it's going to be more basic at the equivalence point, don't you think? Because you're adding a strong base to a weak acid. But if you're adding a strong acid to a weak base, your equivalence point is going to be more acidic than this because you're adding a strong acid, right? So again, if this is an ACS style question and they gave you a titration curve or something and they asked you like, what are you dealing with here? The first thing I would look at is the equivalence point. But not only would I look at the equivalence point, I would look at the shape of the curve, right? These are both S-shaped curves. Yes, they are. But if you're starting at a pH that's basic, you already know that you're titrating a base. The question is, are you titrating a weak base or a strong base? The only way you know is you look at the equivalence point. If it's not 7, then you know it's a weak base. If the equivalence point is 7, then you know it's a strong base that you're titrating. Okay? Likewise, if your initial pH over here is low, you're probably starting to titrate an acid, but is it a strong acid or a weak acid that you're titrating? Well, look at the equivalence point. If the equivalence point is 7, you know you're titrating a strong acid. If the equivalence point is not 7, you're titrating a weak acid, right? right? These are the kinds of things you need to think about, right? Conceptual, guys, conceptual. Don't try to think too much about the numbers all the time. Don't think about this like robots. Oh, I'm plugging stuff into equations and all of that crap, right? Really think about what these graphs are telling you, because on the ACS exam, like I said, you only have a minute 20 seconds. These are the kinds of problems they would ask you. It doesn't make sense for the ACS exam to make you go through an entire ICE table calculation for a titration. They might ask you to do that. I hope they don't. But, to me, a reasonable titration question that's going to last you a minute 20 seconds is really more like analysis of a titration curve, right? Like kind of like how I'm analyzing it here. Think about it like that. Okay. All right, here's a practice problem related to what do you call it? Titrations of what looks like a weak acid, right? HNO2. Remember, HNO2 is a weak acid. HNO3 is a strong acid. Don't confuse that. This is a weak acid, and it's titrated with KOH. KOH is a strong base. So now you're going to calculate. What do they want you to calculate? The volume required to reach the equivalence point. Well, we know how to do that math. I showed you over here. So let's conceptually think of how to do this. First of all, the first thing we want to know is what? How many moles of weak acid are we even starting with before the titration? Here's the calculation, right? You take the amount of liters you have, right? 40 milliliters, multiply that by the concentration of your acid to get the moles of acid. There it is. And then you check the ratio of your weak acid and your strong base. In this case, it's a 1-to-1 ratio. We can prove that by, saying HNO2 plus KOH makes what? Water and salt, KNO2. You balance that equation, you realize everything's a 1-to-1 ratio, so you need as much base as you have acid to neutralize them both, right? And remember, the equivalence point is the amount of base that you need to neutralize all of your acid. And it's a 1-to-1 ratio, and there it is. This is the amount of KOH that you need. And if you're trying to figure out the volume, because this is moles right now, if you need the volume required to reach the equivalence point, then you just need to multiply by the concentration of your KOH, which in this case we show right over here is just 0.2. And there it is. There's your volume of KOH, 20 milliliters, to reach the equivalence point. Let's look at part B. So part B is asking for the pH after 5 milliliter addition. I showed that on the right, that work on the right over here. So how do we do this? Well, the first thing we need to do is figure out how many moles of KOH are in 5 milliliters. Right? We've done this before. Just take, your volume, multiply by your concentration. There's the amount of base that you're adding to your 40 milliliter weak acid sample, and you set up a reaction table, right? This is not an ice table, it's a reaction table. And at first you have no base, and you have that amount of acid, right? We calculated this from here, right? That's the amount of weak acid that you're starting with, and then this is the amount of base that you're adding, right, in 5 milliliters. And now you're figuring out how much of your weak acid ate up all of this, right? It ate up all of this base, and this is how much weak acid you have left. And your weak acid converted to your conjugate base as it ate up this strong base. So the amount of HNO2 that got consumed has been converted to the conjugate base, which is just the same amount of strong base that you added. Okay? We've seen all of this before, right? This is just a different problem, but we've seen this process before. Now we have a ratio, a certain ratio of weak acid and conjugate base. And you know that when you have some ratio of weak acid and conjugate base, you can use the Henderson-Hasselbalch equation. And you just plug those numbers in and realize we're plugging in the moles, not the concentration. We don't need to, because the total concentrations for both acid and base, the total volumes of your weak acid and your conjugate base are going to be the same. So they're just going to cancel each other out. And how do we get the pKa? Well, this would have to be given to you. And I know I didn't give this in this practice problem, but you can imagine that this practice problem, or any other problem I would give you on a quiz, exam, or even on the ACS, they would give you the Ka at the very least of this weak acid, and you can get the pKa, and it turns out to be 3.34. And you can now do the math to get the pH. It's going to be 2.86 after a 5 milliliter addition. Now, part C asks you for the pH at 1/2 the equivalence point. So just think about that. If your equivalence point is 20 milliliters, 1/2 of the equivalence point is going to be 10 milliliters, right? Half of this. And the question is, how much base do you have at 1/2 the equivalence point? And you can basically do the same math and the same logic to get the pH from there, right? Same exact math. Instead of 20 milliliters or 5 milliliters, you're using 10 milliliters, right? So it's all the same. Okay, so now you've seen this in lab. I don't know if you all remember this, but you had to titrate a diprotic acid. And when you titrate a diprotic acid, first of all, what is a diprotic acid? A diprotic acid means an acid, weak or strong. I guess in this case it's weak. Basically, a diprotic acid is an acid that has two dissociable protons. Right? You guys see this is H2? I should say ionizable protons, not dissociated. Ionizable. So bottom line is you have two H's to give to a base. Two, not one. We were used to seeing one, but if we have two here, the first thing that happens is the first one dissociates, or ionizes, I should say. The first one's going to ionize into H plus and HSO3 minus. And there's the Ka for the ionization of that first proton. It's called Ka1. And then the ionization of the second proton in a diprotic acid has its own Ka as well. Okay. Now we can do this titration curve, and what we'll notice is that we have two equivalence points now, not just one. The first equivalence point is when all of the first acid is consumed. All of the first H in our H2SO3 is consumed by a base. So that's going to give us our first equivalence point. The second equivalence point is when the second H plus in our diprotic acid is all consumed. Okay? Now you can probably guess this, that the half equivalence point, where's the half equivalence point? That's when the pH is equal to pKa, right? But the first half equivalence point is going to be pH equals pKa1. The second half equivalence point is going to be when the pH is equal to pKa2. Okay, same idea, it's just you're dealing with more than one ionizable proton, right? When you're dealing with a diprotic acid, you're going to have two equivalence points. If you're dealing with a monoprotic acid, you're just going to have one equivalence point. Okay, so that concludes that lecture. If you have any questions on this, you're more than welcome to email, and I'll be sure to reach out and reach back out and answer. But thanks.